Hi everyone, welcome to LifeSpa1.com where we prove ancient medical wisdom with modern science. And today's LifeSpa podcast, where Ayurveda meets modern science, I have a special guest, Dr. Gerald Pollack, and you're going to be, I think, really thrilled to hear what he has to say about water. If you'd like to watch this podcast, please check it out on your iTunes or your podcast app, and you can get our free podcast available monthly here at LifeSpa1.com. So let me introduce our guest today. Dr. Gerald Pollack received his PhD in biomedical engineering from the University of Pennsylvania. He joined the University of Washington faculty, is now the professor of bioengineering. He's the founder-in-chief of the journal Water, which we're going to talk about today and sort of blow your mind about what water is. He's the convener of the annual Conference of Physics, Chemistry, and Biology of Water, and the executive director of the Institute of Venture Science. His interests range broadly from biological motion and cell biology to interaction of biological surfaces with aqueous solutions. His books include, he's got 3 of them, Muscles and Molecules, Cells, Gels, The Engines of Life. And his newest book, which is the one I recently read, which I highly recommend, is The Fourth Phase of Water, Beyond Solid, Liquid, and Vapor, which we know there's another phase of water that is the most interesting of all, it seems. So that's what we're going to talk about today. Dr. Pollack is the founding fellow at the American Institute of Medical and Biological Engineering and a fellow of both the American Heart Association and Biomedical Engineering Society. He's received many prestigious awards and has presented 2 TED Talks on water, and you can find out more at Pollack, P-O-L-L-A-C-K lab.org, polacklab.org. Dr. Pollack, thank you so much for being here. As you know, what we talk about here with our guests is ancient medical wisdom with modern science. Obviously, water, which is your specialty, is something that's been around for a very, very long time. A lot of ancient wisdom in water. And I'd love to maybe have you start out by telling us a little bit about your newest discovery, the 4th phase of water, and what is that?
Well, thanks, John. Thank you for having me. It's a great pleasure. Our latest discovery. So, we grow up thinking that water. We learn in middle school that water has 3 phases: a solid, ice, a liquid, and a vapor. However, it's been unclear for 100 years or more than 100 years that those 3 phases can explain all of the observations, including scientific observations about water. And so more than 100 years ago, Sir William Hardy, who was a famous colloid chemist, suggested, this was over 100 years ago, suggested that there must be a 4th phase of water because given the 3 phases of water, you can't explain all the observations on water. So something is wrong. You know, most of us have a tendency to dismiss those observations that don't fit the prevailing theory. We call them anomalies. So anomalies is a convenient way to just sort of brush them aside and into a separate category. But what it really means is the theory doesn't work. It doesn't explain these facts, these observations. And I was hugely influenced by a scientist whose name is Gilbert Ling, who came from China. He was in the first group to come from China after World War II. There were 3 of them, and Gilbert is now 99 years old. And another of the 3 won the Nobel Prize in Physics. That's Yang. And so these were really special people. And Gilbert, after doing massive studies and even more massive experiments, understood that there was something different about the water that's inside the cell. You know, we think of water inside the cell as a liquid, but everybody knows who's cut open a cell in biology class that if you cut open the cell, the liquid doesn't pour out. It's gel-like. And Ling concluded that inside the cell, the water molecules must be oriented in some way, must be aligned, and that would be perhaps not called a fourth phase of water, but a kind of liquid crystalline arrangement of water. And that's where we started. And what we found in our experimental evidence is that it was not just inside the cell, but all over, wherever you have water. Whenever the water meets a surface, particularly a hydrophilic or water-loving surface, where if you have such a surface, if you were to drop a droplet on that surface, the droplet would spread out instead of balling up like on Teflon, for example. Those are the kinds of surfaces where if the water meets the surface, the water changes extraordinarily from its usual structure to this so-called fourth phase of organized water. And it's not just a single molecular layer that meets the hydrophilic surface. It's actually, we found in our experiments, up to millions of layers. So it's not, it's macroscopic. You can actually see it with this zone with your eyes under the right conditions. So it has several interesting properties. The first to mention is that it's the water that pretty much fills your body. And as you pointed out, it's maybe the most interesting of all the phases of water. I think it is too. That's the first point. The second point is that it's charged. Water, H2O, is neutral, but this water is charged, and typically it has a negative charge. And if you start with the surface, then this fourth phase water, and then ordinary water beyond that, the fourth phase typically has a negative charge, and there's a positive charge beyond, complementary positive charge. So you've got negative charge in the fourth phase, and positive charge beyond, and that's like a battery. So this water contains energy. By the way, if I refer to it as EZ water, EZ, which I do all the time, EZ is short for exclusion zone. A colleague from Australia suggested that name, and in a way it's appropriate, in a way it's not. The exclusion zone, the first inkling that we had such an ordered zone was that when we took a gel, or we took a polymer that's hydrophilic, and we put water with tiny particles or spheres, we call it microspheres, right next to it, these microspheres were excluded from the liquid crystalline zone. It's just like when ice forms, it pushes out everything else, so you get pure ice. In this case, it excludes pretty much everything, so you get a pure liquid crystal. So it excludes this stuff. So we call it exclusion zone, or EZ.
So this is, can I ask you a quick question about this? So what you're saying is that this exclusion zone water is sort of the body's natural water purification system, because everything that's not water gets pushed out into this sort of bulk water zone area, and you're left with this, which is positively charged, and you're left with this negatively charged exclusion zone that sets up a negative and a positive energy potential. All you got to do is connect those two and you have electricity, right? Is that accurate?
Oh, that's exactly right. Yeah, we could connect them in the laboratory just by putting taking two wires, putting one in that negative zone, another in the positive zone, and connecting them through a little resistor, and you get current flow from the positive to the negative, just like an ordinary battery. And this battery, I might add, you didn't say it, but this battery contains a lot of potential energy, and it's unclear how much, but I think that a large fraction of this energy is actually used for us to do whatever we do. We need energy to do it, and the usual understanding is that this energy is chemical energy provided by ATP, a kind of thought to be universal molecule that has a high energy bond. But after discovering this potential energy from all the charge that is stored in the EZ, or in the fourth phase, this is potential energy, and it can be used, and I believe it is used in our bodies. So I know I'm talking too much, but
no, you're talking great. I just want to add one thing, or ask a question. I think a lot of people have been told that water, H2O, is such an incredible molecule, you can't break it up. that it's impossible to break up, and that's why water is water, and that's why it covers the earth in such quantities. So what you're saying is that it does break up. And
absolutely, and I'm not sure. I'm not sure where that information comes from that the water never breaks up. Maybe some of the chemists or physicists will say that, but it's well known that it does break up. So if you think about photosynthesis, where light strikes the green plant or light strikes the bacterial cell or such, in the case of the green plant where you have chlorophyll, what happens is that the chlorophyll absorbs the light. It acts as a kind of antenna. And step one in the multiple step process that is photosynthesis, by the way, some of the steps are not at all well known, but step one is the breakup of water into H plus and OH minus. So this is accepted by, as far as I know, by all biologists, that light hitting the plant cell mediated by the absorption through chlorophyll, what it does is it splits the water next to the chlorophyll. Now, this is not so different from what we find. In fact, I think what we find could be a generic form of photosynthesis, of the first step in photosynthesis, because we found that the energy to break up the water actually comes from light. Light strikes the water, which is near some interface. It strikes it, breaks up the water into OH minus and H plus. And the OH minus is gathered together to form this fourth phase or exclusion zone, which actually turns out to be, as far as we understand it, a hexagonal sheet-like structure with sheets piling up upon one another like a stack of sheets of paper, like a ream of paper. So I would challenge the assumption or presumption by many people that water can't be broken up into its component parts. It can be, and I give you two examples. One is the photosynthesis, and the second is exactly what we find in the laboratory. So it can be broken up.
So you said hexagonal. So that exclusion zone, which is mostly OH negative, it's a negative charge. Is that all crystalline in nature? Is it structured like a crystal? Is that what's going on?
Yes, it's structured like a crystal, and we know that because of optical studies, studying using polarized light to measure birefringence. And birefringence is a kind of optical feature. It occurs when there's order, and this one is definitely ordered. So we know from the birefringence studies that it's ordered. And in terms of the hexagonality, we've deduced this from several clues. It's not so easy to actually peer in and see those hexagons because they're obviously so small. We're talking about a fraction of a nanometer. And there are techniques like diffraction that can be used to determine it. And there also are some imaging techniques. And a lot of people who have studied water next to interfaces, what we're talking about, have found some hint of hexagonality. Hexagonality pervades nature, and these people have discovered next to various surfaces some kind of hexagonality. The problem is that their methods allow the study only of maybe one or two molecular layers next to the hydrophilic surface, and so it's difficult for those methods to actually to measure what's going on over thousands, hundreds of thousands, or millions of layers. But there is one study that was done by a Harvard group where they looked at protein-encapsulated spheres of water. These occur naturally in biology. And they use electron diffraction, and they concluded that the water actually is ordered inside these spherical structures. And based on the nature of the diffraction pattern they got, they could conclude that they're sheet-like layers of a honeycomb hexagonal structure that actually stack. So I was pleased to see this because it fits exactly with what we're suggesting. So we don't know, 100% whether this is true or not, but based on the evidence, it appears to be honeycomb sheets that stack upon one another. That's the structure of the fourth phase, or easy.
So what you're saying, I'm sure everybody's thinking right now, okay, there's this exclusion zone where it's this purified zone of negatively charged water, and there's this positively charged zone which has got all the kind of particulates in it, and the stuff that the cells like is the negatively charged, clear water in there. So the more of that we have, the better we function, right? So how do we, I'm jumping ahead, I know, but we'll come back and fill in the details, but how do we get more of that easy water?
Yeah, well, okay. So, yeah, you're jumping ahead, and this really relates to ancient medical practices, which is this is what we're after, so we ask ourselves, since this negatively charged easy water is so it's critical for life. So let me start with that point. See, inside the cell is crowded with macromolecules, large molecules. It's so crowded, there's actually not much space for water. Every water molecule is pretty near one of those surfaces, and those surfaces tend to be mainly hydrophilic. And so from that, you can surmise that pretty much all the water in the cell is going to be easy water, which in turn means that every protein inside the cell is surrounded by easy water. So when you think about a protein, you really should be thinking about a protein plus the easy water that's sticking directly to it. Together, those two make up one unit. It's not just the protein that sits in a vacuum or something, it's the protein that sits in easy water. So, okay, so when the protein does its job, what's its job? Well, it depends on the particular cell. So in a muscle cell, the actin and the myosin proteins surrounded by easy water need to fold in some way, from an extended shape to a folded shape. But it's not just the protein, it's the protein plus the easy water that surrounds it. That's the familiar territory to the protein. It folds naturally with the easy water surrounding it. Now, if you don't have enough easy water, if you're dehydrated, if your cell is dehydrated, the two are equivalent, right? You're missing water inside the cell. And since the cell contains mostly easy water, you're missing easy water. So now the protein wants to fold to do its job. And it sees itself surrounded not by the usual envelope of easy water, but nothing or less that's necessary. So it finds itself in a confused environment, and either it may not fold at all, or it may misfold, and therefore, if we're talking about a muscle cell, it's not contracting very well. If we're talking about a nerve cell, it's not communicating information very well. Your brain may be foggy, etc. So what you want to do to promote health, and the ancients knew this in some way, to promote health, is to build that easy water. Okay, so the question boils down to, how do you build easy water? And there are half dozen different ways to do it, which are not very complicated. One, which was maybe you might say favored by the ancients, is to take a walk on the beach barefoot, or to walk barefoot. So what does walking barefoot do? Well, it connects you to the earth, okay? And by connecting you to the earth, and of course the ancients lived that way, well connected to the earth. They didn't have rubber-soled shoes that insulated them from the earth. By connecting your body to the earth, you're connecting your body to a vast reservoir of negative charge. Why negative charge? Well, the earth is negatively charged. Now, I got to admit, I was originally a student of electrical engineering, and if someone had told me that the earth had a net negative charge, I would have said, you're crazy. Not one of my professors ever mentioned anything like that. And I think it was because my professor didn't know. And if I were educated in Russia, probably I'd know it, because my colleague, friend who worked in my lab for a while, Andrei Klimov, one day as he was departing for Moscow, he was in my lab standing right near the door, and he started talking about the Earth's electric field. I said, Andrei, you must be talking about the Earth's magnetic field, because I never heard of an electric field. He said, you never heard of it? It's impossible. He said, in Russia, every middle school student knows about the Earth's electric field. So he retorted by muttering something about the deficiency of the American educational system. And of course, I was a bit skeptical, because how could it be that someone educated in electrical engineering never ever heard that the Earth had a big net negative charge? So I went home scratching my head, and the next morning, one of my students came to me with one volume of the 3-volume set produced called Lectures in Physics by the great physicist Richard Feynman, who many people know. He was not only a great physicist, but he was funny, had great jokes. And he was at Caltech, and someone recorded his lectures and compiled all that stuff into a book. And my student opened it up to volume 2, chapter 9, and there it talked about the Earth's electric field. And the electric field is caused by negative charge in the Earth and positive charge way up somewhere in the ionosphere. So you have positive charge and negative charge, like a capacitor, with an electric field that runs between. And so the field lines run perpendicular to the surface of the Earth. At any rate, the Earth is negatively charged. So sorry for that long diatribe, but so what happens now is you take off your shoes and you take a walk on the sandy beach or on the grass in your backyard, and you're connecting yourself to the negative Earth. So what that means is that if there's any deficiency in negatively charged EZ water, the electrons are going to come and target themselves to that place in your body. And the arrival of electrons, negative charge, means that it will convert the neutral water into negatively charged EZ water, and you're back to health again. So, so this is method number one, and I guess I don't know if it was really known to the ancients, but the ancients would do it every day, and maybe that's one of the ways that they kept healthy, by infusing this negative charge into your body. There's quite a literature on this right now, and a lot of people know this technique very well. And there's one kind of amusing example that a colleague told me about George Washington. So George Washington apparently traveled with his physician. I don't know if he was paranoid about his health or whatever, but whenever he went anywhere, he took his family doctor or his personal physician or whatever. And one day he wasn't feeling well, and his doctor said, "Hug a tree." So as the story goes, he hugged the tree and he felt much, much better. And so why would hugging a tree, as simple as that, make you feel better? Well, the tree, just like us, has negative charge, but the tree has more negative charge. Its cells are not don't have an electrical potential of minus 60 or minus 70 millivolts, but more like minus 200 millivolts. So it's a real source of negative charge. And if we hug the tree, we're connecting ourselves to that negative charge, and negative charge flows into our body, and we build more EZ water, and we feel better. Because whatever cell is responsible for creating our illness or our problems, it's going to get reversed by this. Okay, so that's number one. You want more?
Well, yeah. One other thing that traditional cultures would do is they take their water and they would put it in the glass pitcher, and they would sometimes a different colored pitcher, and they would put it in the sun before they would drink it.
Yes.
Now, I would imagine that must have a big boost of EZ water. Is that true?
I think so. In fact, we've been attempting to get started on experiments like that, because one person in my laboratory, Abha Sharma, is from India and knows much of the Ayurvedic tradition. And she told me that her grandfather used to do this, put pictures of different colors, right. and the sun is beating down, and depending on what particular issue or illness, or she would drink one or the other. So we'd like to follow that experimentally, light. So that actually should build EZ water, and it brings me to...
We did that. We did a study with that, because that's what we practice and talk a lot about here is Ayurvedic medicine. And one of my children's experiments for middle school was to wrap a red filter and a blue filter around water and then put it outside and see which one froze first. The theory was that the red filter would reflect the red, right? Is it the opposite color? It would and let the blue in. So the red would actually let the blue in. Is that true?
Well, it transmits the red. So if you put a sheet of red glass and look at the sun, for example, the red wavelengths come through and all the others are blocked.
Right. So we found that one of them froze a heck of a lot quicker than the other one did. It was pretty interesting. So we did that for you. So you will write it up for you and send it to you. No, I'm just kidding.
That's interesting. Yeah. Well, it's so light. Absolutely. That's why, for example, going out and standing in the sun, which so few of us do these days because everything seems to be indoors. We feel good, and particularly, I live in Seattle, and Seattle is in the winter months tends to be gloomy. We get a lot of cloud cover, a lot of a moderate amount of rain coming from those clouds, and if the sun peeks through at one point, everybody feels happy, and so we tend to attribute that good feeling to some sort of psychological issue, and it may be, but also the light that comes through builds easy water, particularly the infrared wavelengths that come through. Infrared, we're talking about longer wavelengths than red. And infrared, a lot of people don't know exactly about infrared. They think it's somehow associated with heat. And all it is electromagnetic energy, same as light, at a longer wavelength and often associated with heat. So it's all around us. If you were to turn out all the lights in your room and use your cell phone camera, you see nothing because the sensor is sensitive to the visible wavelengths. But if you were to whip out an infrared camera whose sensor is sensitive to infrared wavelengths, then you'd see a beautiful image even though it's completely dark. And that's because everything is generating infrared energy. So we'd be able to see you, your shirt, your tie, the pictures behind you, et cetera, et cetera. Well, everything is generating it. And because everything is generating infrared energy, and infrared energy is what builds most strongly the easy water, because it's available, it's really free energy. We learn about free energy in chemistry class and from textbooks, but this is literally free because it's there all the time. It's free for the taking, and which means that infrared energy is also there. So anyway, if we go out in the sun, we get this energy directly from the sun. It hits us. It builds easy water. Now there are other instances where you can build easy water, and I think the ancients used these as well, and that is the sauna. You know better than I do how old these are. I don't know how old they are, but I bet
very old. Yeah, very old.
Finland, Russia.
Absolutely.
Yeah. So you get in. It's hot, very hot, either humid or dry, and you expose yourself to infrared energy. So that infrared energy hits your body, gets absorbed. Different wavelengths get absorbed more than others, and builds easy water in your body. And that's why after 20 minutes in the sauna, followed by a cooling shower, you feel energized. I've had that experience myself multiple times, and I suppose that the ancients must have done the same. It just feels good to do that. Okay, would
an infrared light be helpful? Is more better in that regard? That's a big popular thing.
Sure it's better or not better. It probably depends on exactly what wavelengths are contained in the infrared light plus the more natural sauna. And I don't know the answer. The manufacturers will know the answer. And so some wavelengths get absorbed by your body more deeply than other wavelengths. And for example, in our studies, we found the wavelength 3.0 micrometers. That is said to get absorbed minimally, but our experiments seem to show otherwise. And that is the wavelength in our experience that builds this water most avidly and most strongly. So if your lamps contain 3 micrometer wavelength, then according to our experiments, it should be very good for building easy water and therefore building function, relieving your pains, your depression, your fatigue, whatever.
You also mentioned that glacier water is really good, and juicing your vegetables is really good.
Yes.
Talk to me about those two things.
So let me first talk about glaciers, and then remind me about juicing. Well, let me start with juicing, okay, and then remind me about glaciers. So juicing, yeah, there are many people dealing with so-called alternative or medicine or has many names, and some of them I know tell me that the simplest way of improving your health is to juice. Now, what's juicing? So juicing is basically taking plants, live plants, and squeezing the hell out of them, squeeze the water out. So what about this water that you squeeze out? Well, the water that you squeeze out is the water from inside the plant cells, right? And this is just full of easy water and lots of negative charge, just what your body wants to be healthy. And so when you drink the water from the plants, hopefully slightly sweetened with the juice of a few strawberries or blueberries or something like that to make it palatable, what you're doing is you're replacing your missing easy water with easy water from the plants, you see. And the report I get from these alternative or integrative doctors is that the patients do really well with this, that they'll come back a few months later, whatever problem, doesn't matter what problem they have, doesn't, water is all over your body, it's everywhere. It doesn't matter what problem, by drinking this water, and I think what that means is restoring the easy water, by doing that, you're promoting function. And the patients come back feeling better no matter what their issue, and they feel more energetic. And also, I'm told that a side benefit is they lose weight. so I think that's another way. And I suppose that way was used by the ancients. You know better than I do, but it's a kind of obvious sort of thing.
Well, for sure. I mean, they ate whole foods and fresh vegetables. Their diet was, 90% plant-based. That's for sure. And then about glacier water. I mean, I studied in India, studied Ayurvedic medicine, and one of maybe the craziest things I ever did was I was in at the source of the Ganges River, and they were talking about how that water was medicinal, had these amazing properties. And I ended up, there was a guy bottling it for the first time, and I ended up buying a container, literally a whole container of Ganges water that I thought everybody in the world would love if I brought it here. And I kind of found out that nobody wanted Ganges water. And I ended up with a container in my garage for many, many cases of Ganges water in my garage for many, many years. And now we boil it and put it on, we have a little product we sell for like spritzer for your face. Thing called Himalayan mist. We put that Ganges water and we still put it in there. But what you're telling us is that there is some special, maybe easy property in when that water goes from ice to liquid form. Tell us about that.
Yeah, okay. So my book contains a lot of information, I think a whole chapter or more on freezing and thawing processes. And they're different from what we think or what everybody thinks. The thought is, well, you take water and the water then converts under the right conditions, can convert itself to ice. And if we take the ice, it melts and goes into water. But that's not quite right. There's an intermediate step. And the intermediate step is if you cool the water, what happens is that the EZ builds, and then it's the EZ that converts into the ice. And if you melt the water, what happens is that the melting process produces EZ water, which eventually becomes a regular water. So that intermediate process is easy. And it's not a surprise completely because the structure of the EZ, the hexagonal kind of structure, is similar to the structure of ice. It's not ice. It's different, but it's not too different from ice. So the experiments, and we have some published papers on this besides the book, show that when you melt the ice, you get EZ to start with. And how quickly it converts into ordinary water, there are many factors involved. So it's not a surprise that the source of the Ganges, with the glacial ice melting, if you pick up that water, it's probably still in the EZ state. See, and then if you drink that water, if drinking easy water is good for health, which you know, everything we've studied points in that direction, then drinking that water from the Ganges would promote health. So one question, of course, is how long does that easy water persist if you just put it into a container? And nobody studied this, but I know from some experiments that we did that persistence could be a very long time. It may be a very stable fraction of water. So, for example, one colleague of mine produces a kind of water that he says good for health. And there are many people who, as you know, who do this. If you search the internet, you'll find many companies selling waters that appear to be good for health. And he told me on the telephone that this water could reverse irreversible kidney pathology. And I said at first that, well, I'm not sure I believe you. Actually, I did. So he sent me hospital records, and it seems absolutely confirmed. And a colleague of mine interviewed some of the people who he claimed had been cured, and they said, yes, indeed, that's so. So I was curious about this water, and he sent me a sample. We were so busy, it just sat on my desk for 3 months. Finally, after 3 months, we tested to see how much EZ water it contained. And it's a very simple technique we use. We know that EZ water absorbs light at a wavelength of 270 nanometers. So we did the test, and even after 3 months, there was a hefty amount of EZ water that was contained in that water. And so, so this is just one experiment to demonstrate that it just doesn't necessarily disappear in a few seconds. We don't know how much EZ water there was at the beginning, but we know after 3 months that quite a bit of it persisted. So it might be the same amount, might be slightly less, might even be more, because if it sits in the presence of infrared energy, the EZ water should build. You see, so it's not true, or not necessarily true, that the EZ will just vanish because it's unstable. It might actually be rather stable. So yeah, I think the Ganges water, it might be that way. And I saw a presentation at a conference, someone who was studying water, the Lord's water, Ganges water, and other waters. And I was looking very carefully at the presentation because I knew what interested me. And in all cases, all of those special healing waters, they contain this same 270 nanometer absorption, which is our indication that they contain EZ water. So it might be that the healing properties of those waters at the source of the Ganges, where it's melting and other places, could be due to the presence of EZ water, just like from plants.
So we haven't talked about too much about what happens to the positively charged, the bulk water, all those protons that are there, and that creates that water battery you talk about. I want to talk about those protons, which I guess are what would actually slowly break down the EZ water, but also I want to ask you about the sodium-potassium pump, which is a positive negatively charged, which is another battery that drives electricity. And of course, that's what every cell is kind of taking in potassium, getting rid of sodium, right? And that creates that electrical charge. How does that relate to this charge that we're creating from the water battery? Do they interact in any way? I'm just curious, because I write a lot about the sodium-potassium pump and how we eat more vegetables to get more potassium, how critical that is, and how we should eat less sodium. Can you kind of tie those together, or are they totally separate things not to be tied together?
No, I can tie those together. So I'm not sure where to start. Sodium-potassium pump was discovered about, well, I don't know, 60 years ago or something like that. And it was then the sodium pump, and it got a Nobel Prize and such. And I believe it doesn't exist. No, it's not necessarily originally my belief system, but it was based on experiments by the guy who I mentioned, Gilbert Ling. So Gilbert Ling, at the time it wasn't known. By now is not just the sodium potassium pump, but the cell membrane is said to contain, if I remember the number correctly, there is something like 2,000 different pumps in the membrane. And Gilbert Ling was skeptical about this about the pump, because pumps require energy. And it was generally known and accepted that 1/3 of the cell's energy is devoted to the sodium pump. Again, at the time it was called the sodium pump, to get the sodium out of the cell in theory. And he did experiments and showed that even if you poison the cell, which is like pulling the plug on the pump, well, it doesn't work anymore. Still, for a very long time, the effect of pumping, or of quote unquote pumping, was still realized. So, there's something wrong there, because it doesn't follow. If you remove the energy and the pump gets turned off, then the effects of pumping should disappear immediately, but they continued for a long time. And Gilbert did calculations on this and showed that in this poison cell, it was just impossible for this pumping to occur, because the total amount of energy that the pump required was, if I remember the number correctly, somewhere between 30 and 100 times the amount of energy that the unplugged pump could possibly muster. They used the cocktails to put every known poison they can think of in the cell, so it really wouldn't do anything, wouldn't pump, but the effects of quote unquote pumping were still there. So he said it can't be. He also brought up, oh, by the way, his objections have never been addressed. They appear in several of his books and articles, and nobody has paid attention to it. See, so it's thought that the electrical potential of the cell is caused by this pumping that you mentioned. And the funny thing is that you can take a system it's just like the inside of the cell, but has no membrane, therefore no pump, and get the same electrical potential. So that is a gel. If you take a gel has no membrane, the cell has a membrane, and you stick the same electrode in the cell or in the gel, the result is pretty much the same. You get a big negative electrical potential. And so the standard textbook theory invoking sodium potassium pump says this is the reason. If that's the reason, then how come you get the same result if you don't even have a membrane or pump or anything like that as in a gel? It doesn't make sense. So if you still want to attribute the electrical potential to the sodium potassium pump, then how do you explain the electrical potential of the gel, which is pretty much the same? You see, so it doesn't make sense. And the final argument, the coup de grace, is by now so many people observing effects say, oh, I've discovered a new pump. That explains my, and as I said, I think the number is now something on the order of a couple of thousand. When Gilbert Ling wrote his stuff, the number was a couple of hundred. Now it's a couple of thousand. And at that point, he said, there's no room for all of these pumps in the cell membrane. Yeah, you see, where are they? And now the problem has gotten even worse because now there's so many more of these pumps that there's no space available for all of them. And then he brings in another point that people have now invoked pumps for substances that are made by chemical companies. They keep cranking out new chemicals, and he says, where's the logic to that? How is it that the cell knows to create a pump for a substance it's never seen before? It's just invented last year by a chemical company. So if you put all these arguments together, I think it's really important to go back and look at the evidence for these pumps. But there's another really easy way to explain the negative electrical potential of the cell, and that is the cell is filled with water. the water is mostly EZ water. EZ water is negatively charged. So therefore, if a cell is filled with negatively charged species, then you're going to have a negatively charged cell. And that's why all cells are negatively charged, because they contain this EZ water.
So
I'm sorry, it's a long answer to a short question, but that part, yeah.
So let me see if I can kind of clarify that in my own head. So we know that if you juice plants, which have hundreds times more potassium than they do sodium, 300 to 1, in many cases sometimes more, and you juice
the cells.
Well, yeah, when you just take the plant and you look at the potassium content to sodium content in the plant, there are 200 to 300 times more potassium than sodium. And at the same time, when you take that plant and juice it, you're also getting more EZ water. You're getting the fluid from the inside of the cell, which is EZ water. So is it safe to say that at least in plants, that sodium, that potassium sort of is directly related to the amount of EZ water, that if as the potassium levels go up in the plant and you eat those, you're going to get more EZ water. So we know that eating more plants gives you better health, lowers blood pressure. Getting more potassium-rich foods gives you better health, lowers blood pressure. But what's really happening, what you're suggesting, is that it's actually not the potassium at all, although that must have some value as an electrolyte. It's actually the EZ water that's actually there in the plant that just so happens to have a higher potassium to sodium ratio. Is that right?
Yeah, exactly. Nobody has ever really come to a clear conclusion as to why there's more potassium inside the cell. But Gilbert Ling argues, and other experimenters have shown, that this potassium is actually not dissolved in the water. It's stuck to the protein surface. See, so it's a little different from, we call it an electrolyte, but it actually may not be dissolved in the water. It may be associated or stuck to the proteins.
Wow, so much we don't know, right?
Oh, let me tell you, I once did a survey about what we know and what we don't know. I was sort of curious. I think my point of view on what we don't know is similar to yours, but I went around the cafeteria at my university, and the people who eat lunch there are mostly biological scientists, and I asked that question. The question was, these are random people who I didn't particularly know. I said, can I ask you a question? Oh, sure. Of all the science that, fundamental science that there is to be known, what fraction do we know? Now, so the answers fell largely into two categories. One category hovered around 2/3. We basically know so much. There are maybe a few things, a few I's to dot, and a few T's to cross, but pretty much we know what's going on. And other people at the opposite extreme said, oh, I'm sure less than 1%. we know so little. And I'm in that second category because I've been in several different fields, and I know that there are accepted points of view in all of those fields, but just simply being accepted, as I gave an example of the sodium potassium pump, is not clear that the acceptance is justified. Many scientists don't like to question their belief systems at really fundamental levels. We all feel comfortable, thinking that we kind of know. There's a sense of stability, kind of knowing how the world works. It gives us a feeling of comfort. And someone comes around and says, like to flat Earth people, says, yeah, it's true. You look out and it looks like the Earth out there is flat, but if you take a more global point of view, it's actually round. And this is, if you pardon the expression, earth-shattering. It doesn't feel comfortable to have our belief systems questioned that way. And scientists are humans like everybody else, and we all like to feel a sense of comfort in our own belief systems. And that's a reason why science is actually, or I should say, reason why we haven't seen very many scientific revolutions in the past few decades. If you ask yourself, it's another question I asked many people. I said to them, can you name in the past 30 years a handful of scientific revolutions, not technical revolutions like the iPhone or something, but fundamental scientific revolutions, like, for example, the structure of DNA, or the splitting of the atom, or the discovery of X-rays, something like that. How many can you name that have occurred in the past 30 years or so? And the usual response is a dumbfounded look, like, oh, I never thought about that question. Let me scratch my head and think. It's really hard for most people to come up with a list of both lay people and scientific people. You know, I've heard of the Higgs boson, which won a Nobel Prize, but you know, how has the Higgs boson affected your life or my life at all? It's a rather arcane sort of thing. So most of the advances in science, and there have been plenty, they're mostly incremental. They're not fundamental like the ones I mentioned. And one of the reasons for that is the way the scientific approach has been institutionalized. So if you want to study the role of ancient Ayurvedic thinking into modern medicine, and you want to apply for money, it's really difficult for you to get it because the people who are doing the reviewing are the experts in the prevailing field. And in your case, it would be modern medicine, and they don't necessarily want intruders like you coming in to upset their belief system. And so it's really difficult for you to get money to continue your research. And a lot of scientists know this, and so they simply refrain from pursuing revolutionary work. They rather do work that is incremental because they can get funding. Funding is absolutely critical for every scientist. They can't proceed without paying salaries to the people who help do the experiments and such.
Right.
So I think I've gotten off track, but
I have a few questions for you. One is, as I was reading your book, I was thinking, okay, what's the best way to make easy water and just hydrate my cells and create more electrical energy in my body? And I was thinking, if you exercise in the sun, where you're getting the sunlight to kind of separate through that first step of photosynthesis, create more OH negative particles in my body. And I was sweating, and sweat is sodium, and that's positively charged, and I'm getting rid of those protons, that the easy water is pushing out all those protons and particulates and toxins in the water, and you sweat those out. So I was thinking, and I'm hoping you can clarify that exercising in the sun to get that first step of photosynthesis and sweating to get rid of the bad stuff would be a really good idea. Maybe drinking some green juice along the way.
Well, yeah, I mean, you need to hydrate yourself. So you played 2 rounds of tennis and you're dead to the world, and you got to drink to replace the water that you've lost. But this is definitely one way of losing protons, because the sweat tends to be positively charged. You're getting actually many things that you do that you do all the time are tending to get rid of positive charge. The one thing is exhaling. So when you exhale, you've got, you're exhaling carbon dioxide in part, and the carbon dioxide and the water together make for carbonic acid, right, which is full of protons. So when you breathe out, you're actually getting rid of positive charge every time you exhale. And as you pointed out, sweating does it too. And going to the bathroom to pee, often the urine tends to be low pH, which means it's acid. So you've got multiple ways ordinary ways to get rid of protons, and that could be one of the reasons why exercise is healthy for you, because as you pointed out earlier, the protons tend to compromise the amount of easy water, and so the body tries to get rid of them as much as possible.
Now we published a study years ago, one of my first books, Body, Mind, and Sport, compared nose breathing versus mouth breathing. And nose breathing theoretically goes through these turbinates and drives the air all the way into the lower lobes of your lungs more effectively, where there's a predominance of alveoli for exchanging waste and getting rid of more carbonic acid, getting rid of more waste, and detoxifying the body better. And we found that when you breathe through your nose, the brain's waves slipped into an alpha state. When you're breathing through the mouth, they flipped into a beta state. We measured parasympathetic versus sympathetic activity. We measured a whole bunch of stuff, and we found out that when you breathe through your nose, the old ancient pranayama technique, kind of only during activity, made phenomenal changes in terms of how we feel. So I'm imagining what you're saying is by getting rid of all those positively charged protons through the acid relief as you detox, that would allow the body to then make more easy water inside. Is that true?
Well, I'm not sure if it will help make more, but it will help. It will reduce the compromising effect of the nearby protons. So we found that, if you have an EZ and you've got a lot of protons nearby, the protons tend to limit the growth of the EZ. It's just the opposite charge. It tends to encroach on EZ. So you want to get rid of those protons as much as possible. I'm not familiar with the studies that you mentioned, but I certainly can imagine that would occur. And anything you can do to enhance EZ water, at least according to our theoretical studies, should improve your health. And so I've given you 4 or 5 different routes so far. And there's one that I want to mention now before we finish, because this does go back to Ayurvedic times, and that is some of the foods, or I should say herbs or spices, like turmeric, for example. So you know better than I do how many thousands of years people have used turmeric.
Big time, thousands, probably 5,000 each.
5,000. Okay. Yeah. Seemed to work for 5,000 years, but we've kind of forgotten. So we did experiments. It was not only on turmeric, but also basil, and a few other substances that are widely known to promote health. It almost doesn't matter what your issue is. If you take turmeric or basil, it should improve. And our hypothesis was that what these substances do in the concentrations that you're likely to have in your body is they build EZ water. So we tested this on a setup. We have a certain amount of EZ water, and then we put a small amount of whatever substance in the water. And by golly, EZ was increased by 20, 30, sometimes even more %. And so by extrapolating to the body, we can envision that taking these substances will build EZ water. And so if you're deficient in EZ water, whether it's your kidney or your liver or your lung or your brain or whatever, it's going to build EZ water. And therefore, whatever pathology you have, which might be caused by a dehydration, that is a deficiency in EZ water, will be restored. And I think this is a very simple paradigm or mechanism by which to gain health. And as you say, it's 5,000-6,000 years old.
Well, we're big believers and use turmeric and holy basil all the time. Did you get a sense of what the mechanism was for that? How it actually created the EZ water?
No, I wish we did, but we don't know. It's not just those substances. We studied a whole bunch, and we just published a paper. It was just last month that it came out. Also, coconut oil, coconut water, and also, well, we studied various fats, ghee, for example.
Yeah, we have a lot of ghee.
Yeah, and this was actually prompted by I don't know if you know Dave Asprey, who is
sure,
yeah.
Of course.
Yeah, Dave was chatting with us about it, and he actually gave us a gift to prompt us to move in that direction. And we did. We haven't published the paper yet, but the results are clear. So we could take some ghee, and we have a way of actually solidifying it. And the ghee, it is basically solidified, but I mean solidified into the shape of a rod. And we put this rod into water and microspheres, and we can see next to this rod of ghee, the microspheres are moving away, leaving a gap, an exclusion zone, EZ, that is as large as we've ever seen. So it means that ghee seems to be really powerful in creating EZ water. and therefore we understand why ghee is considered, again, 5,000 years, 6,000 years.
Oh,
I don't.
yeah.
Yeah,
Amazing. Yeah.
good for health. It makes total sense, and the mechanism seems to be in the buildup of easy water. And since easy water is throughout your body, necessary, it means that ghee should be good pretty much for whatever ails you.
Wow, that's just amazing. I'm always so fascinated, which is why I write about ancient wisdom and modern science. How did they know thousands of years ago to take milk and boil off all the milk solids until you ended up with just the oil of ghee, which happens to have like the highest concentration of butyric acid, which we have microbes in our gut, Clostridium butyricum, that literally makes butyric acid to heal your intestinal skin. Yeah. Yet they knew, and now we're finding out that the ghee actually supports the hydration of the cell. Did you happen to measure other oils like olive oil or other oils as well, or processed oils, and see the difference?
No, we haven't done that, but that's kind of on the agenda. See, in order to do a proper study, we need something that's solid, and so some of these oils are not, and it makes the study more challenging. But
you did do coconut oil. You said you did coconut oil, and that worked.
Yeah, coconut oil, but it tends to be solidified. And coconut water we did also, and that dissolves in the water. And we found that it increases the easy size. So yeah, I mean, you've now turned me on to which ones would you suggest we look at?
In terms of what? Well, I think there's a big debate about, when you take, polyunsaturated fatty acids have been bleached and boiled and deodorized in a significant fashion. You've taken all the nutrients out of that, and it's just as pure oil, which the body, that's why they put in a loaf of bread, and the loaf of bread will stay on the shelf and stay squishy for a month because the bugs won't eat it. You put it inside of your body, the bugs won't eat it, suggesting that if they won't eat it, where does all that oil go? Directly to the garbage can, which is either your lymph or your liver, and that congests your liver, causes bile issues, and we have a whole bunch of gallbladder surgeries every day. And so that would be like a bad taste of oil. But there's a lot of people saying that all oils are bad. And I'm like, yeah, maybe, but ghee and coconut oil and olive oil, that's sort of my question is, it's not really that natural to just press an olive and make oil out of it. Ancient humans probably didn't do that. And when you start doing that stuff, are we actually creating a problem? Or like in the ghee, it looks like we're creating a solution. And what's the problem? Where's the solution is sort of that question. What oils are good? What oils are bad? It's very interesting because, in the 1950s, when they took cholesterol out of our diet, they replaced it with polyunsaturated fatty acids, and heart disease went up. And a lot of problems went up. So it didn't solve the problem because those oils were so processed that our bugs wouldn't eat it and ended up congesting our livers, creating a lot of liver problems. So that's sort of where we ended up. So I'm just so fascinated to hear that the coconut oil and the coconut did support that. Obviously, people lived on that for thousands of years. And the fact that ghee was so supportive, I think that's fascinating. I'm sure Dave Asprey asked you to do coffee too, right? What did coffee come out with?
Well, we haven't studied the coffee part yet, but yeah, I know in the case of Dave Asprey, the bulletproof coffee is touted as health promoting, and perhaps it is. Maybe we do need to study coffee as well.
Coffee and the ghee together, yeah, fascinating.
Yeah. So there's just one more that I way of building easy water that I want to mention before I know we're reaching the end, but that is hyperbaric oxygen therapy. I don't know if you're familiar. No, so this is not something used by the ancients, and so maybe we should not discuss it. But
no, good, go for it.
Yeah, I think it's interesting. So this is just a great big chamber into which you immerse your body, and it's sealed, and you get high oxygen under high pressure. And at first, it was used for wound healing, for the military, people who had gaping wounds that wouldn't heal, but you put them in this chamber and they healed. And so one of my former students, or actually was a postdoc with me in my lab, after he finished, he went to work for a company that not only produced these machines, but was doing research. And we had lunch together after a few months, and he came back and he says, you know, Jerry, it's funny, this device was invented for wound healing, but by now looks like there are some 30 different syndromes that benefit from hyperbaric oxygen therapy, HBOT. And I said, well, tell me. And so he went down this long list, and he said, well, it's difficult to get FDA approval for these, but the research has shown that it works. So we scratch our heads together. If it works for so many different syndromes, either it's got to have 30 different mechanisms, or it's got one mechanism that operates in 30 different places. And, you know, by Occam's razor, it seemed natural. The simpler explanation was that it's one mechanism. And so thinking of one mechanism, you know, what is it, what that's all over the place, and that's water. So we came up with a hypothesis to start with, that what hyperbaric oxygen therapy does is increases the amount of easy water. A student of mine, a very talented undergraduate, took up the project. He looked at easy under the presence of high oxygen, as in HBOT. Sure enough, it built easy water. And then high pressure, sure enough, it built easy water. So when you put the two together, high pressure, high oxygen, you should get a super buildup of easy water. And we published that study. I can't say that it's drawn a lot of attention, but I think it's possible that that hyperbaric oxygen therapy, the reason it's as effective as it is because it builds easy water throughout your body, everywhere. And my wife is on it right now. Unfortunately, she's suffering with stage 4 ovarian cancer. And, and one of the therapies, you know, that is highly recommended by the integrative practitioners is indeed hyperbaric oxygen therapy. And every time she goes in, she comes out, she feels better. So we're hopeful. But that is yet another way, according to our experiments, to build easy water.
Would ozone or O3 have any positive or negative effect? Do you know?
I don't know. We haven't tried it. Can't say. Sorry.
Yeah. Well, this has been nothing short of fascinating, and I know that we have just touched the surface on what you know about the 4th phase of water and this easy exclusion zone water and how important it is for our health and for the cells and to hydrate your cells. I really encourage everybody to read Dr. Pollack's book, The 4th Phase of Water. He goes into such great detail about every way that this water seems to apply itself to our health and to like ankle swelling and all these amazing things. It's just an amazing journey. I just loved reading your book, and I don't think we touched the surface on what you know about this, and you know we didn't, and I apologize for interrupting you and asking you a lot of questions, but I know my readers want to know, how do I get this water in my body right away? And I want to go buy the water. And is there a product out there, an easy water product that you would recommend or not at this point?
Well, I tend to avoid recommending anything because I need to remain independent of any particular product. And we also don't test products for that reason, because if the test is pretty good, there's an implicit message that I'm standing behind that, and I prefer to remain independent of any commercial product. And so, but there are products out there that claim to have 4th phase or easy water.
In general, would high alkaline water be more beneficial?
I think so. Yeah, because high alkaline water has a lot of negative charge. We think of it as having high pH. Our measurements show that, yes, high pH, but also high negative charge. That water is actually charged with net negativity. And we tried some experiments a few years ago with alkaline water to see if indeed they contain easy. And for some reason, we didn't find it. However, someone in my lab just last week said they tested another batch of it, and absolutely it does contain. So I think it should. I'm not sure. We have to study some more, but I suspect it's probably rich in easy water.
Once again, the more we know, the less we know, right?
Well, yeah. There's a lot of information coming out in science, but that doesn't always lead to more understanding.
Well, anyway, Dr. Pollack, I want to thank you again. I want to encourage everybody to get his book, The Fourth Phase of Water. Get more information about the work he's doing at Pollack, P-O-L-L-A-C-K lab.org. You can check him out there. And you can also watch the LifeSpa podcast every month for free on your on iTunes or whatever podcast app you're using. Check us out, LifeSpa, Ancient Wisdom Meets Modern Science. Thanks all for listening, and we'll see you next time.
Thank you, John. Appreciated your great questions. Okay, take care.
Very welcome. Do you like this video? Don't forget to subscribe and share.
This recording is brought to you by LifeSpa, where ancient Ayurvedic wisdom meets modern science. Get access to free health video newsletters by Dr. John at LifeSpa.com. These statements have not been evaluated by the FDA. These products are not intended to diagnose, treat, cure, or prevent any disease.